Okay, so today we will discuss isolated DC-DC converters. There are several types of isolated DC-DC converters, such as you might have studied forward converter, flyback converter, push-pull converter, and so on. Um, Mostly we will talk about forward and flyback converter. So about that converter, we will discuss. Uh, yeah. First of all, we should know that both of all of the isolated converters work based on transformers. Without transformer or without isolation based on transformers, we cannot operate such kind of DC-DC converters, right? So, is it a good idea to proceed with the basic concept of transformer, or should we just dive down into flyback and forward converters? I want your opinion. Yeah,
Sir, we can go into transformers, sir, but we can discuss about the flux in the core.
flux in the code. Okay, so I will discuss about flux, and basically I will take some time initially to describe the transformer operation, and after that we will proceed with the converter. I think that should be fine. Yeah. So the basic drawbacks with our DC-DC converters are they are conductively coupled to each other, primary and secondary side. So because of conductive coupling between them, there are certain drawbacks. First thing is that no, you cannot achieve a certain higher gain. Like if you will go with the ratio of transfer function of output to input, you will face certain challenges to achieve this ratio of more than two in case of boost converter per se. So for boost converter, so you cannot, there are not much flexibility in our output and input relationship. And further, whatever some faulty or some damages happens on the load side, that will be directly reflected to our source side. So for that purpose, if we provide certain isolation in terms of transformer or galvanic isolation, so that will protect our circuit. Further, it also give us the flexibility to achieve our output to input relationship with a wide variation. So that we will see. And so let me first draw a transformer. So this we will assume as a primary winding where we apply a sinusoidal voltage or AC voltage V1, and we get and we have some second where we will receive as a voltage which should be function of V1. So for an ideal transformer, you will see. Let us assume its turns is N1 and its turn is N2. So number of turns will vary, and the relationship between V2 and V1, what we generally see. And if you are from electrical background, you might be knowing that this is the ratio of N2 by N1. Generally, we do not write V2 by V1 is equal to N2 by N1. Generally, it happens to be E2 by E1 is equal to N2 by N1. Whatever the EMF that induced, so let me write the formula for EMF. So that generally comes out to be 4.44 F phi N. So here F is frequency, phi is flux, and N is your number of turns. Okay, so whatever EMF that will be induced in the winding E1 and E2. So this EMF will be the function of frequency, flux, and number of turns. And from this formula only, we can write E1 by E2 is equal to N1 by N2. When we can write like this, so given the condition that our frequency and flux in the core are constant, right? So then only we can say that this relationship will be valid, right? And further from this point, if we assume that first let me draw an equivalent circuit diagram, then it will be easy to visualize in terms of drops. So when we describe concepts in terms of electrical parameters, so it is better to draw certain electrical circuits. So as we have given some supply in the primary side, so with voltage amplitude of V1, and there will be some primary wire resistance, so we can denote it with R1, and some inductance L1, and there will be some magnetizing inductance, right? Why magnetizing inductance? Could you explain that, anyone? What is the importance of magnetizing inductance? Here, this will be your turns, winding turns of your primary transformer, and this will be secondary side. And this symbol, that parallel lines, they denote that they are isolated with each other. And as we move towards the secondary side will again have some resistance and inductances. Why? Because of secondary side also has a winding, and winding must have, winding is made up of some wires. So wires should have some resistance and inductance. And wires are made like a coil. They are wounded. So when it get wounded, it will create, if you flow certain current inside the wire, right, in certain manner. So your current direction, if you curl your hand in that direction of current, you will see that direction of flux you will achieve towards downward. So this will be the flux flow direction, and this is your current. So when we flow certain current to the coil, it will produce certain flux, and same thing will happen on the primary side as well. If you curl your fingers in the direction of current, you will be able to visualize the direction of flux in such direction. So that winding will have inductance as well as resistance. And here the voltage, let me first write the induced EMF, that is E1 in the primary winding, and induced EMF secondary winding is E2. Here dots are important. I will discuss the significance of these dots, how to place the dots. So L2 and R2. Okay, so I had coded one question earlier. What were that? Ah, Yeah, anyone want to answer that question?
Because current through that inductor is responsible to produce the magnetizing flux.
Uh, uh, Magnetizing, yeah, you are correct, but partially you are, I would say, not clear. Uh, the other way is that magnetizing inductance is the way of the representation. Okay, so
It's a
to
mutual inductance.
yeah, yeah,
It's a
go ahead, say.
mutual inductance.
Mutual inductance, yeah, you can say, but my purpose behind asking the question that what is the working of LM, and why to denote the LM in the circuit. So that should be there should be some significance of LM in the circuit, right? So what it denotes, right? So that's what I wanted to ask. Oh, okay, no issue. So you are almost there. Whoever answered that, I think Adesh. So you are almost there. In LM is magnetizing inductance is a way to represent how much flux is required to operate the transformer, right? So transformer will have certain supply, and since it is inductively connected, primary and secondary side, so there are no conductive coupling, so there must be some flux so that it will couple both the sides, right? So that flux, to establish that much flux, how much inductance should be there? Okay, in ideal transformer you would not see that magnetizing inductance, because we assume that in an ideal transformer it is an infinite permeable material, so we do not need an magnetizing component of current to prepare the core as a medium to couple via the flux, right? So let me tell you in terms of currents as well or parameters, then it will be more clear. So let us suppose uh, our input side,
Sir,
we are draw. Yeah, yeah, go ahead, please.
sir, you said this LM is directly connected with the permeability of the core.
Yes,
Sir, in ideal transformer, we say it has infinite. The permeability is infinite. The
yes,
relative permeability is infinite.
infinite.
Uh, sir, is that relative permeability of the core, and this LM is directly proportional.
Yes, yes. Yeah, inductance is proportional to permeability, right? If you see the formula of inductance, mu naught mu r n square A by L.
Okay.
So if your permeability is infinite, let us suppose mu naught is fixed anyway. So if mu r is infinite, then your inductance will be infinite. Then you can treat it as an open circuit, right?
Okay, sir. Sir, that inductance is only this LM, not this L1.
No, L1 is a leakage inductance. In transformer, there will be certain leakages that will happen. If you let me, so if you will apply certain supply to the primary winding, flux will flow, but it is not guaranteed that all your flux will travel through core only. Some flux will leakage through the airs also, right?
Sir, is that mean the leakage inductance is proportional to the permeability of the air?
Yes, yes, you can say.
Okay.
So in that case, what about the actual inductance of the primary winding itself? That is not need to be considered.
Actual inductance of primary winding, you mean
Yeah,
that
the
wire
coil.
inductance?
Yeah, the wire inductance.
Yeah, yeah, that is there. See, let me draw the equivalent circuit, then it will be. R1, L1, and it start. Yeah, anyone wants to say something? Please go ahead.
Sir, no, sir. Actually, when the flux leak, the leakage flux,
Mhm.
instead of flowing through the winding, it will flow on the copper wire that is wound on the core. Will that mean that leakage inductance is directly proportional to permeability of the copper material or air?
No. Leakage flux will not flow through the copper wire because to flow through the wire, actually generally wires are insulated, right?
Yes.
So if it will be to flow the flux, that
The
material should be such that it
No,
allow
sir.
the.
No, flow means I am not saying it is flowing through the conductor. It is cutting the copper conductor.
Okay, yeah. So indirectly it is cutting the air only because coppers are generally placed in air, right? Even in the core, the copper wires are wound along the your steel core or whatever is that. So you can, as whatever the permeability of that material, let's say your copper has certain permeability, then you can consider that into account. But generally we ignore that because that would not be significant. To consider equivalent to air, that would be more than sufficient.
Okay, sir. We can go to the previous question. What are the other points?
So here we induced L1. In primary inductance, you can add all the practicality, leakage inductance, okay, wire inductance, or any other inductance you want to include, right? So that L1 equivalent we call, here your all practical inductances will be incorporated in the equation, right? But that would not be very significant compared to your magnetizing inductance. Generally, our magnetizing inductances are high in quantity compared to all other inductance.
Yeah. Okay. So
So, so why LM? Coming back to the question. So I was telling that once you apply this, certain power supply, you will draw certain current, right? And that current, if the same current will go to the output side, it means you do not need to establish the flux in the core. That means, let us suppose if your transformer is an ideal or ideal transformer, we say core permeability is infinite. It means power is equal to Vi, whatever we are giving from the input side. Let us suppose V1 and I1. That will be your input power. Now I1 will have two components, right? One will be active component. So let us call it as
IW.
IW, yeah, working IW square, and one is magnetizing component. Okay, so it means when your core permeability is infinite, it means you do not need to give any magnetizing component. So whatever you do, and all power will be active power. And what happens when all power becomes active power? What happens to the power factor?
One. Unity.
unity.
One. Yeah, correct. Perfect. So that will be one. Right? So it means your supply size should not increase for the given power if your power factor is unity. Right? But practically, this is not the case. We generally require some magnetizing component, and that is typically our no load power factor becomes 0.2 to zero point 0.4. So this is the range of no load power factor. So let us not go into that. That is not the topic. So that's what I wanted to mention here. So as you add the load on the secondary side, So
Sir,
yeah, go ahead, please.
sir, that in the previous explanation about the total inductance, you said
Mhm.
the total inductance seen from the source is the sum of leakage inductance plus magnetizing inductance plus some wire inductance. Is that what you have said, sir?
Apart from magnetizing inductance, since I am talking about L1 and I have explicitly defined Ln, right? So I cannot include Ln. I am just talking primary inductance apart from magnetizing inductance, only leakage and wire inductance.
Okay. So, sir, seeing from the source, LM also will be taken into account.
Yeah, yeah. If you will compute equivalent from this point,
Uh,
then your Lm will come. But I am just talking about this L1 equivalent,
okay.
not L equivalent.
Sir, I have one more question.
Yeah, yeah. Go ahead, please.
Mm, Sir, in the turns ratio that we have previously written that E2 by E1 equal to N2 by N1.
Mhm.
You said that relation comes from the EMF equation that 4.4485. And
Mhm. Yes, yes.
so similarly, how does the where does the current relation come? We will write N1 by N2 equal to I2 by I1.
Yeah, yeah. Good question. So, see, if we are assuming E1 is equal to V1, right? E1 is equal to V1 when the drops are neglected.
So, leakage inductance is zero and resistance is zero, primary
Yeah.
one.
So when drops are neglected, it means E1 is equal to V1. Now, again, we are assuming that our transformer is 100% efficient, lossless transformer.
Okay,
Then only we can say that V1 I1 is equal to V2 I2,
okay,
right? So V1 by V2 is equal to I2 by I1 equal to N1 by N. Okay? So this is again based on assumptions.
Mhm. So we assume that this is an ideal transformer, we are writing this relation.
Right.
So
And in
for
practical transformer, see, this we drawn here practical transformer. So here this I1 and this I2, because after this point, no any dropping elements are present. So here we can say I1 by I2 is equal to N2 by N1. You cannot say
yeah, so in this point it is
this
an yeah.
this I and this I2, right? Yeah.
So this is an ideal transformer. For the ideal transformer, we are adding all these non-idealities.
Yes.
That's
Okay. So just for the clarification, so let us suppose your flux is in this axis and IW and EMF, and to establish this flux phi, you will require some magnetizing component, IB or IW, what you call it. So your resultant current will be somewhere here, right? So ideally this I should be on y-axis, but now due to magnetizing component, you will get current somewhere in the middle, and that angle will be phi. So this is the power factor angle. So here, if you calculate active power, E into I to cos phi, and I cos phi particularly, it will become IW. That will be your active power. That will be transferred to the secondary side, right? Any other question from the basics? So if we further simplify it, we just need to know we have primary winding, because in power electronics we will not deal with leakages and all. We will deal with only ideal transformer, and we will represent it as our in primary supply and our secondary supply.
Sir,
Here, yeah, go ahead, please.
sir, this I cos phi, EI cos phi, you are saying this is the real power transfer,
Yes,
real or active power. Sir, but
active power.
this I cos phi is the current which is responsible to produce the uh, hysteresis and eddy current loss.
Yes, yes, you're
Uh,
correct.
uh,
And not only I, total, not only I cos phi, total current. Oh, sorry. Yeah, IW only is the responsible for your hysteresis and eddy current. Yeah, go ahead, please.
uh, Sir, if so, so this P is the actual active power transferred from the primary to secondary side.
Yes.
So is that mean the active power transferred is nothing but the power lost in the eddy current and power lost in hysteresis and eddy current?
Yeah, if no loads are there, if it is open connection, then whatever the active power is there, that will be your no load losses. It means iron loss, and iron loss has two components: eddy current losses and hysteresis current losses. So, let me complete the working of this transformer. So, as soon as you connect a load here,
Mm. Okay.
as soon as you connect the load, it will draw the certain current, right? And this current will increase. This I2 will increase, right?
Yes. Yes, sir.
And as this current will increase, its demand, or by even by turns ratio, it will from where it will draw the current from primary side only, right?
Yeah.
So it will draw.
Or
Yeah,
we
go
can
ahead.
say this reflected current will also increase.
Yeah. So as soon as you loaded the transformer, your I2 increase. It means your I1 will increase. Okay. And if your core is saturated or your flux is proper to operate the working, your IM is same, right? IM, whatever it was there. So now your IM is same and your I1 is increased. So your power factor will also improve. And as you increase the I1, now your working component IW will have two components, right? Not total, or not all the amplitude of working current will go into losses. Certain proportion of that current will go in losses, iron losses, and one additional loss will be there, copper loss, right? So when you have significant current and you have winding resistances, you will have some losses in the winding resistances, and that will be copper loss, core loss, and whatever load is required. So load power. So when we compute efficiencies generally, P out by P in. Okay. So in output, whatever's V naught, V, V naught means output voltage, I naught means output current. Okay. Or just not to confuse, V2, I2 cos phi divided by input. Input will be output plus losses, right? So cos phi plus iron losses plus whatever the load is there. Let us suppose if it is operating at full load, then it will have copper losses, right? This loss will be the function of load. If let us assume your transformer is operating at 70% of load, so then we write it as X is equal to Pi by, and this X will go in here, but I don't think you need to know that much concept of transformer as of now, since we are talking in terms of power electronics. Otherwise, I would have explained, but there will be no benefit of this point. So just understand that there will be certain losses along with your load power, right? So that's what was your question. I hope that that answers your question.
Yes. So this copper loss occurs in the primary resistance and the equivalent secondary resistance.
Yeah.
And this iron loss occurs in hysteresis and eddy current. And this is the power delivered to the load, V2 I2 cos.
Yes. So in chat box there are certain questions. So what is IW? IW is nothing but the active component of your current. Okay, that is delivering the power to the load. And in flyback lecture notation, N is used and said as turns ratio is N1 by N2, but in see there are some misconception about turns ratio. It is generally most of the standard books they use turns ratio as N2 by N1. So we try to follow. Otherwise, if there will be something else as a turns ratio, then it will be mentioned explicitly, right? If someone wants to compute in terms of N1 by N2, they will explicitly mention. Otherwise, you go ahead with your course instructor, what they are saying, right? So, for this course particularly, I would recommend that you follow this trend only. If turns ratio are written somewhere without mentioning anything, you just understand that it is talking about N2 by N1. And all terminologies are same: transformers, transformation ratio, turns ratio, whatever you want to call it, right? Because if you see from the secondary side, you will see that your primary is getting transformed from secondary side. So there are no a standard rule, but most people assume that turns ratio and transformation ratios as N2 by N1. I think we should stick with it. Otherwise, in most of the exams, they explicitly mention it that you assume turns ratio at N2 by N1. I do not think any confusion should be there. Okay, so when I1 increase, Im is equal to constant. Why? See, if your core is working at the rated flux, right? So to operate at rated condition, our flux should be rated and our current should be rated, right? So once you maintain the rated flux in the core, then there is no need to further increase the flux, right? Now you are just connecting the load. Load means you are just connecting the whatever kind of supply do you want to cater. Okay. So now that load will require additional current, that load current, but your transformer is at rated flux. So if it is at rated flux, Im will not increase. You will not want to increase the Im because Im is already at its rated value. Now, if you increase it further, your power factor will deteriorate, right? So you do not want to deteriorate the power factor of the machine. Is it clear, Jagdish? Okay, thank you. So I think we should go ahead with the discussion. Yeah, so just let me clarify about dot convention. Okay, so let us assume this is an ideal transformer. You have given a supply here, and you are placing certain dots in the circuit. So what does it mean? It means you assume any dot for the reference, and here the whatever voltage will appear, that will be in the polarity with the similar to your supply, right? And this same voltage will appear along the dot connected to that winding, right? So this V1 will be connected here in this fashion, and that will be equal to V2 minus V2, right? So V1 will become minus V2. Or I think to avoid the confusion, let me write E1 and E2. E1 and E2. So E1 will be equal to V1. E2 will be equal to E1 if, or let us suppose N1 is to N2 is turns ratio here. So E2 will be E1 into N2 by N1. Okay. Now V2 polarity is opposite of E2. So V2 will be equal to minus E2. This was about voltage. Now coming to the current, if we are following this dot convention, then current must enter the first dot, okay, I1, and it should come out from the other dot. So this will be your I2. So that here on primary side, current is entering the dot, and on the secondary side, current is coming out of the dot. Okay. So that should be the convention we should follow. Any question about that?
Sir, convention, you mean if the current entering the primary dotted terminal is positive, then the positive, I mean, if I draw the waveform, I will draw the waveform of I1 above the horizontal axis.
Yes.
Uh, so by positive convention, if the current in the secondary leaves the dotted terminal, then that direction of current flow through the secondary can be treated as positive.
Yes.
So if I draw the waveform, I can draw the I2 current waveform also above the horizontal axis.
Yes. Yes. Convention means we are taking one as a reference and now treating according to the reference thing, right? So that's what we mean by.
Okay, sir.
Okay then. So I think now we should move on to the flyback converter. Non-isolated converter we have learned. Current and output. Okay, so we will see the relationship between input and output current in isolated converters as well. As we will move ahead, we will derive those equations. And anyway, if you have two converters and it is mentioned that it is lossless and you know the voltage relationship, you can at any point of time you can say that current relationship is opposite of that. So if V naught by V in is equal to N times D, let us suppose in forward converter, then you can say that I in by I naught is equal to N times D, given that your converter is lossless. Okay, so we will see further the relationship between them. So we will talk about flyback converter. So here, and when we are talking about isolated converters and when we are introducing certain transformers, then we have to deal with high frequency, right? Why I am saying this? Anyone?
So what is the question, sir?
Yeah, so I asked, whenever we are dealing with isolated DC-DC converters, we must deal with high frequency. So do you know the reason behind this? Did you get the question first?
Yes, sir. Why we are operating high frequency when we use uh,
First of all, do you agree that we need to operate at higher frequency?
Yes, sir. The reason is to reduce the size of magnetics.
Correct. That is the justification of using high frequency. Otherwise, if you will move ahead with low frequency, such as 50 hertz or 100 hertz, you will have to connect very large magnetics. So you will lose all the advantage of using DC-DC converters. So
Sir,
here, yeah, yeah, go ahead, please.
sir, is there any relation which explains that when frequency increases, the size of transformer or inductance come down, or it is just that x equal to 2 pi f L that?
Uh, yeah, so there are certain derivations by which you can visualize this result that how size gets reduced when we use uh, higher frequency, right?
Yes.
And there are many physical examples as we use switches uh, in our regulator and fans. So they are high frequency devices and they are very small. And earlier we used to have, our typical regulators that used to be heavy inside. They were low frequency. So you can visualize it physically by observing things as well. And there are certain derivations as well. So you might want to refer some textbooks for that, and you will definitely find the derivation of relationship between frequency and sizing of the component. So this is a typical flyback converter. From input, you will give supply to certain transformer. Okay, some EMF will be induced in primary as well as secondary. How it will induce? By the help of flux, right, and number of turns. So this windings will have certain number of turns, and as you draw certain current, okay, so it will create certain flux in the core. As you will have current in this direction, so you will establish certain flux in the core, and hence it will work as a your isolated DC-DC converter. Now breaking it into further or simplifying it to the circuit so that we will not have to draw every time this transformer. Okay, so we will represent it as with a magnetizing inductance and our number of turns, right? So your supply. So we are ignoring the primary resistances and inductances, even secondary as well. So this will have your number of turns N1, and here we will write it as I1. This is IS. Now we will reverse the polarity so that we will achieve our desirable switching performances, right? So intentionally we have reversed the direction of polarity here so that when the switch is on, only one action will happen. Our magnetizing inductance will get charged, and when switch will be off, it will get discharged, right? So intentionally we are putting dots in such a manner so that we will achieve our switching performance. So by observing this circuit, are you able to recall any particular conductive coupling DC-DC converters?
It's a buck boost, right?
Buck boost, yeah, perfect. So it is similar to buck boost apart from this isolation. Right? So you can expect relationship between output and input similar to the buck boost. Just that number of turns will be induced. So this is your IR, and now, okay, I forgot to connect the switch. So now when switch will be closed, okay, what will happen? Your magnetizing inductance will get charged. Okay, so let me draw the equivalent circuit when your switch will be closed. So just let me copy it and you'll be able to edit. So when your switch will be charged, sorry, when your switch will be closed, here across V1, let me denote it as V as V2. Since we have reversed the polarity, we should treat it as according to polarity, right? So wherever dot is there, since in the primary, wherever dot was there, we placed positive polarity of supply. That's why we should follow the trend, and in secondary also, wherever the dot is present, we should present the same polarity as the primary. So we ended up with this kind of polarity, right? So when this switch will be closed, our V1 will be equal to Vs.
Yes.
Now, by the property of transformer, let us suppose N1 and N2 is the turns ratio, V2 will be equal to N2 by N1 to V1. Okay, it means 2 by N1 into Vs. Now, negative of the voltage is connected to the anode of the diode. So, your diode will be off till the time the switch is on. Right? So, we will remove the diode for this period. Now, when switch is closed, IC will be equal to minus IR by KCL, we can say. Okay. So, and your inductance Lm is getting charged with the slope V1 by Lm. Di Lm by dt, you can say V1, which is equal to Vs by L. Similar to our conventional buck boost converter. Any doubt in this? To get the relationship between output and input, what we needed to do in earlier converters, we applied volt second balance. So the similar thing we have to here as well. Which bottom way, anywhere you can place switch. Doesn't matter. As long as this switch is connected in series with the supply, you can place it anywhere. Now, when switch open, or 1 minus t into t period. Okay, so now we have loaded the switch. And yeah, one thing I forget to mention, when your diode is off, then certain voltage will appear across the diode, right? So that voltage should be, that diode should have the capability to withstand that amount of voltage. So for that computation, we will have to apply a KVL, right? So we, we are applying a KVL in this loop. That should be 0. So VD equal to V2 minus V2 minus V0, and V2 is Vs into N2 by N1, and V0 is that we will derive from volt second balance relationship between V0 and Vs. So, and anyway that V0 will come positive. So if you see overall voltage across the diode, and that is coming out to be negative, so it means diode is your off. That's one way of indication. And the amount of voltage that it needs to block, or it needs to withstand the capability of minus Vs into N2 by N1 minus V. Okay, so that's how we compute the capability of switch, blocking capability of switch. Since our primary switch, this S1 is on, so we do not need to compute at this time. But when it will be off, during off period, we will compute that as well. Okay. So now when switch is open, this magnetizing inductance, it will release its energy. Okay, because it will have path, it has some certain energy, it has got charge to certain peak value, ILM peak. Now it needs to discharge, and it has only one path. It should flow like this. Okay. So, and here certain voltage will appear, and that we will see how much. So now our diode is connected, and we will have certain voltage in this fashion. And here we have V2, N1 is to N2, and here we had V1. So V2 from this side, if you see, V2 is equal to minus V0, right? And V2 by V1 is equal to N2 by N1. So we can compute N1 from this relationship. V2 into N2 by N1. Right? And V2 is minus V0, so minus V0 into 2 by. So here the voltage along the inductance is now coming out to be negative, and that is VLN, let me write, minus V0 into N2 by N1. So that it will be discharged along the primary winding, or your inductance current will fall down. Right? The slope of the inductance current will be negative. So that's what we infer from this relationship. Any doubt till now? Okay, so I assume it is clear till this point. Our purpose was to compute the relationship between output and input.
So this is N1 by N2, right? V1 equal to V2 into.
V1 is equal. Ah, yeah, you are correct. One by n. Thanks. So now we will compute by volt second balance. So when switch was on, our VLM during on was Vs, VLM during off minus V naught into N1 by N2. Okay, we'll apply volt second balance and VLM dt 0 to 3 equal to 0. So Vs into dt plus minus V naught to N1 by N2 equal to 0. So,
into 1 minus dts should be there.
yeah, yeah, correct. Thanks. To 1 minus is as we compute V naught by V, yes, we'll get D 1 minus D into V naught N2 by N1. So, yeah, I think, yeah, this is all. So, this is what we get the relationship between input and output. And this N2 by N generally we refer as N turns ratio. So, let's say V naught by Vs is equal to N to D by 1 minus D. This much relationship, I think it is familiar to us. Right? Only one additional parameter N introduced because of the transformer turns ratio. And with this introduction of N, we can get the range of this transfer function is very high. So we can achieve even with 100 volt of input, we can get 5 volt of output, and even with means variation. What I mean to say, variation will be very high. So we will have large flexibility in relationship between output and input. So if yeah, any doubt there?
Sir, here we are discussing about the flyback converter.
Flyback converter.
Sir, suppose in the you have said this n varies from n gives us the flexibility of going from any least value to higher value.
Mhm.
Since it is a buck boost based flyback converter.
Yeah.
Similarly, if we have in the forward converter, the same n will appear. Uh, mm, so in that case, uh, sir, is that range limited to less than the input voltage only or output voltage?
No, 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 no. In forward, as
Because
though you are getting n into d, but as you increase the number of turns ratio, or sorry, parameter of turns ratio, you will get even higher than input in forward converter.
okay, so even though it is buck based, we can get higher voltage.
Higher because of the n, not because of d.
Okay, so there also the range is some any some minimum value to maximum value some.
Yeah, yeah, there also range is quite flexible.
Oh, So in both forward and flyback, we can get the same range of output.
Yeah,
If
similar
if
range.
we if we
You
keep
should not say same. You will get similar.
uh, okay.
See, these are just topologies which got famous. Okay, in power electronics there are number of topologies, but people do not generally use. People
Mm,
tend to use these two topologies particularly because they were easy to implement, and they have been they have been being implemented for quite a year. So once some benchmark is fixed and that is quite accessible to many people, and there are not major drawbacks to that, people
mm,
generally do not shift to certain new things. People will look for new things when the new thing is giving certain advantages, which you know in in every aspect. So then only people will tend to shift. Otherwise, why would anyone shift?
yeah. So sir,
So,
we can say in both the topologies we can get voltage which is lesser than the input voltage and greater than the input voltage also.
yeah, definitely.
Sir,
Yeah, yeah, go ahead, please.
uh, is this topology is best suitable for high voltage, low current
High voltage, low current, this topology.
output?
Yeah, yeah,
Normally, the previous TV high voltage generation was made with this type of this topology flyback. But
yes.
whether it is CCM or DCM, that is not disclosed by the designers.
Because there is no such significance of CCM and DCM. Uh, until and unless you are getting your desirable outcome, you
Hmm.
should not be concerned with CCM. It is just to solve the problems and to design the circuit. So with DCM, you are able to design it a good power electronics converter. Why would you bother?
But which transformer is size-wise bigger or lesser, CCM or DCM for the same output rating?
Um, that we will have to solve certain with given design parameters, because once you keep the frequency fixed, then size of transformer will be fixed. So for that purpose, we will need to compute the frequency, and it will depend on the converter. So for what value of duty ratio, since you fixed your number of turns, then you will have to compute the frequency of that converter. So it
But
might appear, yeah, yeah, go ahead.
if the controller are there and controllers with the variable frequency as well as variable PWM from the same controller is available for
Yeah, yeah,
the
you can vary that with with controllers. You can certainly vary the frequency.
uh,
Variable
variable
frequency,
frequency and variable PWM that is available there.
yes, yes.
Okay, not only PWM.
Not only PWM. There are certain controllers
Controllers
like,
are there. They can work in variable frequency as well as variable PWM,
yes,
and they
yes.
are best suitable for this type of topology.
Yeah, if you want to control the frequency, or if
Mm.
you want to change the frequency in the converter, then those topologies would those controller strategy would be handy.
Do you know type of control, specific name of the controllers which are having this type of? Because 3842 and 44 series are having fixed voltage, fixed frequency PWM controllers,
Yeah.
but the current mode controllers are having both frequency as well as PWM. If you
Right.
know, please suggest us.
Definitely. As of now, I am not able to recall the name, but I will look and I will tell you the name of controller in the next.
Then the whole CCM and DCM is possible. I think so. If they,
Uh, it should be possible. It should not be any issue of using CCM or DCM.
mm.
But as you mentioned that you were not able to see whether the converter was CCM or DCM. So generally, manufacturers do not disclose that it is DCM or CCM, because it is no it is of no use to us to as a consumer.
as a consumer. But what designer, it is very much essential, because if it is CCM, then the load variant is very much absorbed and duty cycle is not going to very much.
But
But for
with the data set, you can estimate whether the converter is CCM or DCM. You will have certain parameters. You can
okay,
compute and you can verify whether it is CCM.
but there is a very large change in the load, then we sometimes we have to work in DCM, sometimes we have to go for the DCM.
Yes, yes, that is also another case. Yeah, you are correct.
For the if we design the control loop for the CCM, it will work for the DCM also.
DCM also. Yeah, it will have to work for certain. If we have variable load, then we
Uh,
will have to make it work as a CCM as well as DCM.
DCM control. Okay. But please suggest us.
Definitely. Yeah. I will
Oh,
come up with certain names in the description.
okay. Thank you, sir.
Thank you.
Please give me the contact number, your contact number, so that I can ask, or is the email ID is there?
Email ID, I think I have already shared, but again, I will share at the end of the session, or if you
Okay.
want, I can share now as well.
Okay. Thank you, sir.
Thank you. So, yeah, so we were discussing, so we derived the relationship between input and output. So now we would like to see the graph of or characteristics of our parameters. Okay, so just let me draw. So first, if we are assuming that it is working in CCM, so we will draw the inductor current waveform with that. Now we want to compute the source current for this converter. So let me bring back the converter. So when our switch was closed, then IS we can say is equal to ILM, right, plus I1. Okay? So if this is the current waveform of ILM, we will have IS will be equal to ILM plus I1 if you apply the KCL. And as I am saying IS is equal to I1 plus ILM, but I will draw it only IS is equal to ILM. Why I am doing that? Do you have any reason? This is ILM peak.
So because when the switch is conducting the secondary, the current is not flowing on the secondary winding. So
Perfect.
load
Yeah,
reflected
yeah.
is zero.
So I1 will be zero when switch will be conducting due to the diode is off. So that's why I am drawing IS is equal to ILM peak. The peak of IS is same as ILM. Now I want to plot the diode current. Do you have any guess for diode current?
It will be zero.
It will be zero for DT. That's correct. Further, it will be ILM, right? Because when our switch is closed, when the switch is open, this ILM will flow through the winding, and this current will be get induced on the secondary side. And since this diode is closed, so this ID current will be average of ID current will be equal to IR, right? So this will again be ILM with turns ratio. Right? Am I correct? Any doubt in that?
No, no.
So here again ILM into N1 by. Okay, so the plot of diode and switch or rather source. Okay.
It is N2 by N1, sir.
Uh, why you are saying okay, right, you are correct. Since we are computing ID, so ID is in and so correct.
Sir,
Yeah, go ahead, please.
uh, sir, this secondary side current that ILM1 by ID equal to N2 by N1, right? If you
See,
write this transformer relation,
yeah,
I
let me write the transformer relationship. ID by I1 is equal to N1 by N2, right?
yes, sir.
Generally, we equate MMF. MMF is ampere turns.
Ampere turns.
So ampere turns is N into I. So N2 equal to N1 into I1. So if you see ID is associated with N2 number of turns, so we can write N2 into ID
Sir, that
is
is
it.
okay. Yes,
Huh.
sir. But from this relation, this ILM peak should have to be N1 by N2, right? If you the peak of ID,
See, your ILM peak is on primary side, right?
yes, sir. That is I1.
I1. So,
Okay.
and we want I2 in terms of
ID.
I1. ID, right?
Yes, sir.
Just let me write N1 into I1 or okay.
Uh,
So I will be ILM N1 by N. Okay. Okay.
so this has to be
No, it is coming other way. Let me just verify it. Yeah, it should be ID IM N1 by N2. Yeah, it should be N1 by N2. It should be N1 by N2. So this is the curve here. Now, anything left?
so
Yeah,
what about IS in 1 minus D?
IS in 1 minus D, it should be 0, right?
So,
Because your switch is open, so it should be.
okay.
Anything we forgot to plot? I think capacitor current. Okay. So when our switch was off, oh sorry, when our switch was on, then our diode was off, right? So, and when diode is off, this IC will be equal to minus I naught or minus IR. And since IR is our DC component, so that creates minus I. And when our switch is off, okay, so when our switch is off, our IC will be equal to ID minus IR. When our switch off, IC will be equal to ID minus IR, and ID at that time is ILM to N1 by N minus, it will follow ILM curve, but with the reduction of the average or IR. So it will follow this ID, and this is the curve of ID. And if we reduce the IR, let us assume this much is IR, then we will get this kind of. Now we have drawn almost everything. Now any parameter is feasible to compute. So first things first, we would like to compute ripple in our voltage. Since we computed ripple in current, and that's how we computed the relationship between output and input. Now we would like to compute the relationship of ripple in output voltage. So again, it is similar to our buck boost converter. This is your charge. So del V not equal to del Q by C. Del Q is nothing but IR to T dt. IR, this is the magnitude IR. We are computing area of this IR into dt divided by time period. So that will be multiplied with sorry, time period we do not require because of del Q is equal to I into T, right? So del Q is I into T, and the time for conduction is dt, and C was already there, so we'll get C in denominator. So IR in T by FC. T is equal to 1 by F. So this is your ripple voltage. The same value should come from 1 minus D period as well. But since it is quite straightforward to compute the area of rectangle, so we should uh, take that convenient path. Yeah, so ILM average, if we compute ILM average, ILM average is, let us see the circuit first. I have copied already. So we can write IS as ILM into D, right? Do you agree with this expression? IS is the current that is flowing when your switch is on, equal to your magnetizing inductor current. That is the statement that implies this expression. Okay, so if you agree, now,
Sir,
yeah, go ahead, please.
sir, this, can you please say this, because this looks like a input output average current relation,
Okay.
but can
So
you
see,
explain?
just I want to convey
Okay.
this source current is the same current going through the magnetizing inductance when the switch is closed, right?
Yes.
So that's what I have written in terms of equation. Is equal to ILM into D. ILM is the current that is flowing for the entire duration.
Okay.
That
Got it.
will be equal to Is only when switch is closed.
Hmm.
So
Yes. In the
let me
1 minus
see.
D, IS is 0.
Yeah. So and further, if we are assuming that this is a lossless converter, so we will equate power. Is is equal to V naught I naught. Just to compute average value of magnetizing current. Is we derived as D into IL, D into ILM equal to V naught into I naught. I naught is V naught by R, is resistive load. you will get ILM is equal to V naught square divided by Vs to D. This is your average value of magnetizing current.
R will come.
Sorry?
The denominator will have R.
Ah, yeah, correct. Sorry for that. Similarly, you can again compute from 1 minus D component as well. If you go ahead with 1 minus D during when switch is off, you will get certain other parameter, or just that V naught by Vs you can put that you will get. Let me write it. Let me further simplify it. So one V naught will be there, one V naught by Vs is there, and Dr is by Dr not by Vs is 2 by N1 D into 1 minus. So this term will be cancelled. Get V naught by R by N1. So anyway, you can compute it. If you do not know the supply voltage Vs, you can go ahead with this expression. Otherwise, you will be fine with first. Now you know the ILM. You can easily compute maximum value of magnetizing current and minimum value of magnetizing current. Okay. So ILM peak will be equal to ILM plus del ILM by 2. This is easy, right? ILM you just computed, and del ILM and anytime you can compute 3 Vs by FL, right? FLM. How I am writing it directly? Just you see del ILM by dt I am writing d by f, and when the switch was on, the voltage across the magnetizing inductor is Vs and Lm is the inductance. So it is quite a straightforward. You just plug in those equations and you will get P. And similarly, ILM minimum, ILM minus del ILM by.
So this del ILM that we have calculated previously, right?
Yeah, we have calculated it earlier as well. But at any point of time, you can compute. It is just one step thing, right? Any doubt?
No, 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 sir.
So this we computed, and to identify uh, the boundary condition when the things will be just continuous. So what do we do for boundary condition?
In inductor, we will calculate del
Yeah.
IL by 2 equal to I naught.
No. This minimum current we equate to zero, right?
Yes.
Yeah. So ILM minimum is equal to zero. It means ILM is equal to del ILM by 2. And in certain case, like in buck converter, it used to happen like ILM or inductor current average is equal to output current, but it will not be fitted everywhere. So,
Okay, sir.
so if you are remembering something, you just see the condition what is there. So you just plug in all the values you have. ILM is by R into V naught square by Vs into dr square by Vs into dr, or you can write it as Vs into d divided by V naught by R into del ILM dVs by. So whatever the value of inductance you will get from this expression, that Lm, that will have the critical value. So that inductance is responsible to make the converter just continuous. dVs by 2f 1 minus R. This will be the value of your critical inductance. Or if you further supply, you will get something like this 1 minus V square. If you plug in V naught by Vs value here, you will get 1 minus V square into 2f into R into here. This is the value of critical inductance. And if you see certain data set, you can visualize if the value of inductance is less than the parameters. If you have the parameters such as load or something, the ratio, you can compute it.
Sir,
Yeah, go ahead, please.
sir, this Lm is the magnetizing inductance.
Yes, yes, magnetizing inductance,
Sir, which is in the transformer.
which is in the transformer. Yeah.
Sir, because then how to make this inductance come across the primary winding so that we can achieve critical
Uh, Come again, please. How to? Can you repeat that, please?
in the boost converter. Sir, suppose in the buck converter, if you are calculating this critical value, if uh, so at the output, if we put this inductance there, the current through the inductor will be just touching zero.
Yeah.
But here, if in the transformer, this magnetizing inductance, it is not a discrete element, right? We can't remove this Lm. Then
Uh-huh.
how to connect this Lm there in the transformer so that we can get the current
Uh,
which is
See, while designing the converter, initially you will have to decide all the parameters. Once you design the converter, you cannot change it. And while designing, you have transformer, you can change the value of inductance by number of turns. You have the freedom in your hand in terms of number of turns, right?
mm,
Number of turns, wire area, whatever you want to change, you can change the value of inductance.
okay. So we have to rewire the transformer to get this critical inductance.
Yeah, not rewire, you can say. If you have already designed, then you have to rewire. Otherwise, if you are designing it for first time, then you can decide, right?
Sir,
Go ahead, please.
this LM critical is going to change as per the load.
LM critical will not change because if you
D,
have,
if it is D is fixed, R is fixed, R
yeah,
we are going to change.
yes,
Suppose
yes.
it is 100 ohms. Next load it will be 50 ohms.
Mhm.
Then is for fix D, fix F, and fix N. Whole thing will change.
It can change, yeah.
Then we cannot put the L critical if it is 100 microhenry for one particular parameter. Then another it will be 200 microhenry parameter.
Yeah,
So
so uh,
how you will fix that L critical? We cannot
uh,
make the L critical fix for the total variation of the load.
While designing the converter, if you want to ensure continuous conduction mode throughout, then you will have to take the loading condition as a word, right? So
Okay.
you will have to take the minimum load such that if for the worst case your converter is not going in DCM mode, then for other cases it won't go anyway, right? So
Okay.
if you want to ensure, you have to design it for worst case.
For suppose for 25% of the full load capacity current level load condition,
Yes,
200% or like that,
yes,
20% or like that. So in that region, for 20% to say 80, 100% load, L critical is suffice going to be in CCM mode, like that. It will happen.
yes. And many times while you design the converter, you will know that for how much operating region it will vary. So you will design accordingly.
Sir,
Yeah, but
we are actually finding this critical inductance to not allow the converter to operate in DCM, correct?
yes.
So as you explained, if you keep this R naught to be R naught minimum while we are designing this LM, then whatever R naught it varies, it will be above, it will remain in CCM. That is it what you are saying, sir? If you keep this R naught
Uh-huh.
R in the equation to be minimum and find this critical value,
Yes,
then even though if you increase R beyond that, beyond
beyond
the
that,
worst condition that we have designed, it will remain in CCM.
yes.
Okay.
The basic philosophy behind that, you design it for worst case, okay?
Mhm.
And if you have designed it for worst case, it won't go in DCM for better load. Right?
Sir, worst case you mean
Worst case, it
or
means if you design a critical value, right? You do not want to reduce this critical inductance,
yeah, beyond that,
right?
below that.
So you should not reduce the value of resistance, or you should not increase the current after that level, right?
Yes. Yeah, if you keep voltage constant, output voltage.
Hmm. Voltage is anyway regulated your output voltage. Okay, so we
Excuse
will
me, sir.
see. Yeah, go ahead.
Here we are taking the inductance of the transformer LM. What about leakage reactance of the transformer? They don't have any effect.
They will have effect. They will add up only. If you will introduce leakage inductance, your overall inductance will add up and it will increase. But just for the simplicity, we are ignoring. But that will have positive impact on you. That's negative impact in terms of drops. But in terms of your inductance, it will increase. So you will require lower size of magnetizing inductance if you will have certain requirement of inductance, overall inductance.
So
Does that
particularly in
answer your
load
question?
condition.
Yeah, yeah, go ahead, please.
In load
Particularly,
condition, in the loaded condition, this
yes.
can we take the referred value to the primary side, the
Yeah,
leakage reactance also?
yeah, everything. We generally take deferred value, not exact value. If you let me go back to that circuit, everything we deal in terms of equivalent or refer to certain side. Yeah, so if this is the circuit here, how do we refer? We will have certain relationships. So let us suppose we have certain parameter R1, L1, Lm. So R1, L1, Lm, and this ratio is N1 is to N2, L2, and R2. Now we will have to take equivalent refer to some side, right? So let us suppose we are referring this secondary to primary. So to the side where we are referring, we will multiply. Let us suppose first let me draw an equivalent. So will be R1 equivalent,
Yeah.
L1 equivalent, anyway Ln. Secondary side will just be there for the representation. Since we have referred everything
Yes.
to N1 is now R1 equivalent will be R1 which was earlier present in the primary plus secondary side
Hmm.
resistance into multiplication with turns ratio square, and that you determine by the way to the side where you are referring to the primary side. So
Hmm.
you will first write to the side where you are referring, that is N1, in denominator from the side you are going, right, into.
Hmm.
So just like that, and here we take a square, not just turns ratio, so that we should take care. And similarly, L1 equivalent equal to L1 plus L2 to the side where we are referring, from the side where we are.
Yes.
So this will be your overall equivalent, and when you will design for certain uh, inductance or you have determined the critical inductance for that purpose, you you might add L1 equivalent plus Ln. Okay, but generally we ignore L1 equivalent because they are very small compared to Ln. So that's why we do not mention in the problems and design. But that will only add up, right? So that is not going to
Okay.
change the circuit condition from CCM to DCM. That will only push from DCM to CCM. It might, not always. Okay.
Okay. Thank you.
Thank you.
Sir, can you upload today's session?
Yeah, within half an hour, I upload.
Okay.
So we computed LM critical. We will see one problem based on this flyback converter. Certain parameter I will write here. Vs is equal to 24 volt, get supply voltage. Okay. Put and output current will be okay. Put and output current. You can directly apply that ratio of transfer function as we mentioned since we are dealing with lossless components. So that denote by this relations. Yeah, so V naught by Vs, that you can put as Is by. Yeah, Ajit. So we are assuming this converter as a lossless, so you can directly write it. But I naught by Is, not I naught by not I naught I1 by Is. Okay, Is is from the current that is coming out from the supply, okay, not the primary winding current. So that primary winding current may differ, but supply current will be same. What about critical capacitance value? Okay, so critical capacitance value also you can derive it, right? Let's go to, yeah. So if you will equate V naught equal to del V naught by 2, you know the V naught, you know the del V naught, and in del V naught expression, capacitance term. So let me write V naught equal to d I naught by FC 2. So AC critical will equal to d I naught is V naught, and V naught by I naught is R. So d by 2F. So this will be your critical capacity. So just similar to your critical capacitance, you can compute for any circuit. Is it fine, TD? I think we shall move ahead to. So yes, see in this problem also N1 by N2 they have given is equal to 3. So most of the time you should not worry, or you do not need to worry about what a turns ratio N2 by N1. You can take anything, but generally in questions it is mentioned explicitly that what is this ratio. LM is 500 microhenry.
If it is only say that the turn ratio is 3, then it
Huh.
should be N1 upon N2
N2 by
or
N1
N2
you
upon
should
N3.
N2 by N1, because you will get question
Okay.
in this course only, and this course instructor has taken N2 by N1, so you should follow that.
N2 upon N1.
Yeah. Capacitance is also given, switching frequency is given 40 kilohertz, and V naught is given 5 volt. Okay, so you are given with almost all parameters. Now the first thing you need to determine the duty ratio, and this is for flyback. So for flyback, you need to compute duty ratio first thing first. Okay, so since we have derived, right, V naught by Vs equal to N2 by N1 to P divided by 1 minus T. So you just need to plug in all those values. 5, yes, is 24, N2 by N1 is 1 by 3, pi d by 1 minus d is equal to 5 by 4 into 3. So to further simplify it, so d 5, 15,
It's converted to 0.06.
0.06. I don't think so, because it is 15 by 39, so it would be less than 0.5, right? 15 by 39, so that's 0.3846. So right, did you get that?
Yeah.
In part B, it is asked to compute magnetizing current, average value, maximum value, and minimum. ILM average, ILM ILM minimum. Okay. So ILM average
Sir,
would
the
be,
last question, N2 by N1 is 3, right? Or
yeah,
N1 by N2?
N1 by N2 is 3. That's why I had to took N2 by N1 is equal to 1 by 3.
Ah, okay, sir.
So ILM average, the best shortest path to calculate ILM average. Any suggestion? With this with these many parameters, what will be the shortest and convenient path to compute average magnetizing inductor current? First thing first, ILM average, we can write it as source current divided by D, right? Or as I wrote it earlier, IS is equal to DILM.
Chaman,
So we computed V naught by Vs, or we were given that V naught by Vs is given 5 by 24, and I naught we can compute from the given data, V naught by R, that will be 1, V naught is this much, R is this much, so I naught will be 1. So we need Is, we computed D, ILM is equal to Is by D, we just need to compute Is. Vs Is is equal to V naught I, right? If all components are ideal, not S is equal to V naught is nothing but V naught by Vs is 5 by 24, correct? 5 by 20, and I naught is 1. 5. So Is is 5 by 24. Now ILM is Is by D, 5 by 20.6846. Compute it, get 0.597 amperes. Okay. Hope you will also get the same value. Now ILM
This
max,
is the average value.
this is the average value. Yeah. You have one uh, work to do. You just verify it with the derivation what we did for ILM, and you match those values. You verify it, and there might be some discrepancy. So that's why I am saying you must verify it, and then you will have to let me know that where we did wrong, if we are wrong. The second thing is ILM max. Since we computed ILM average, we'll have to add del IL by 2 here, and del IL is nothing but dVs by FL. I think everything is given. 2.597 plus dVs by 2 FL will be there. 2.85 is D, 2 Vs is 24, 2 into frequency is 40 kilohertz. Ln is given, yeah, 500 microhenry. We will compute first this parameter del IL by 2. It is coming out to be 0.231. Hope I am correct about it. So,
Yes, sir.
okay, thanks. So if you will add 8, 7.88 ampere, that is peak value of magnetizing current. Similarly, minimum value of magnetizing current is 0.597 minus this value, that is del IL by 2. It's 0.366. This is all about this problem. And last thing is to compute output voltage ripple. Okay, that is not a big deal. Del V naught, third part. So del V naught computed del Q by C, and during when switch was on, uh, current through the capacitor was minus I naught, right? So if you can visualize the graph of that circuit of Liebeck converter, when your switch was on, your diode was off, and your capacitor was directly connected to the load. So if you apply the KCL at output node, you will get IC is equal to minus I naught. And the charge is the area of that curve. So I naught into dt divided by C d I naught by F. D we compute 0.385 into I naught was 1 into frequency is 40 kilohertz. So capacitance was given 200 micro. You compute
200 microns,
200 micro. Oh, yeah,
0.048.
0.048 you are getting.
Yes.
Okay, so I think should be correct. Let me verify. Get 5 divided by 0.48. So
0.48, sir.
this 0.48%, right? Sorry, wait. 0.0481. This much is the value. And if you want to compute in terms of percentage, right? So in question it was asked percentage of voltage ripple. So del V naught by V naught will have to 0.0481 divided by V naught 5 volt. That will be
0.9.
9625. That is the ratio, and convert into percentage 0.96. So ripple is quite fine, 0.96% for the given capacitor. So this is the type of question I think Today we are only able to cover flyback converter. We did not touch forward. Next session we cover forward as well. So this is all about today's session. If you have any final questions, we can discuss it. Otherwise, we will wind up the session. And yeah, I will give my email ID and this is my email ID. Can you once again show voltage across switch? The blocking capability, you mean, Azit? Okay. I think that point I did not discuss. Blocking capability of the switch. So, see, when the switch was closed,
Yeah,
sorry, when the switch was open, so minus plus. Why I am taking this polarity? Will replace it with buck converter. You switch here, place it here. Your polarity was the switch. So this is the polarity of yes. Oh, now you apply the KVL with switch. So plus VSW minus plus, sorry for the confusion, plus VSW plus minus VSW minus yes and minus V1. So you will apply. Basically, if you apply the KVL, switch voltage will be equal to minus of your supply voltage and mine. Uh, yeah, it is correct. So it will be plus V1. So I will clarify it once at the end. So and V1, uh, uh, if you have achieved somewhere here, V1 is equal to minus V1 by N2 minus Vs minus by N2. So the blocking capability of the switch should be supply plus into.
N2.
So this much is the capability. So see, here V1 was positive. So if we apply KVL, minus V switch minus Vs, that is supply voltage, and plus V1. And plus V1 is equal to minus V0 into N1 by N. Again, it will be minus. So that's why both get added and we end up with Vs plus V0 into N1 by N2. And that is in negative. So that much capability it should have to block the voltage. Any doubt?
So it is 39 volt.
39 volt. You are telling me answer for certain thing?
Yes, for VN 24 plus 5 into 3 by 1.
Yes. If you refer to that problem, you can easily compute. That is 24 plus V0 was 5, N1 by N2 was 1 by 3, right? N1 by N2.
N1 by N3 is 3 by 1. No? N2 by N1.
Okay, just let me verify it. So, N1 by N2 is 1 by 3 given in the problem. So turns ratio is 1 by 3 if you see in that way.
Hmm.
So you computed it with 3, that is also fine. You might got confused with that. But in given data, it was 1 by 3. So you get 24 plus 5 by 3 and whatever it is, 25 points. Yeah, so I will upload my notes in the Drive. You can access that Excel sheet, right? Google Sheet. In the Drive folder, I will upload the notes as well, Kusan. You can access it from there. So this is all. Any final doubt before winding up the session?
Sir,
Yeah.
sir, we have found the voltage test across the switch and it is off. Sir, when it is switching off, when it is trying to switch off, when the switch, at that time, the voltage spike is appearing across the switch,
Okay.
which is greater than this value.
Which is greater than this value when
If
we
suppose,
are switching on the switch, right?
no, sir, when we are switching off,
When we are switching off, the switch will see higher than this voltage you are telling.
yes, sir, at the moment of switch off,
Uh-huh.
uh, since the inductor voltage is reversing, at that time, uh, if the voltage is higher than this actually the capacity, the voltage across the switch will settle down to this value of 25 point something, but at the instant of switching off it will be of higher value. uh,
Okay.
it
So, uh, yeah. So, if it will have certain higher than this, then we will have to design according to that value.
sir, actually why that higher
Here,
computation,
here,
actually why that waveform appears, sir, because uh,
Okay.
it should
So
not happen, no, but it is happening.
it okay. So
so here,
Because,
N1 upon N2 is 3.
N1 upon N2 is 3. Yeah.
So it should be V naught 5 into 3, no?
Uh, yeah. N1 upon N2. Just a minute. Just a minute. Not N1 by N2. Yeah. So earlier you
So
computed that was correct. Yeah. That is 5 by 3.
15 plus 24.
Yeah, that will be 39. Yeah, so it should be 30. Sorry for that. So RS, you were saying when we do switching on or off, we see a spike. So there are certain regions for that to observe such as spikes. So first we need to know the region, or many times we eliminate those regions. Otherwise, if those regions are still there, then we try to design the switch according to the spike level of voltage.
yeah, sir,
So
in forward converter also, uh, during the flux reset, when the diode and resistance are
yes,
conducting, so at that time the switch sees a spike in voltage
yes.
when,
Oh,
so
yeah, it happens.
I don't know
Spikes,
why that comes spike,
a spike occurs, I think, due to that uh,
because if that
high
with that
high D, high di by dt maybe appears. There
sorry,
are certain
if that spike we have, then we have to select a switch with the voltage getting higher than that spike value.
yes.
So
Uh, but
Sir,
there are Go ahead, Rakesh, please.
this yes, sir. This switching frequency will be limited by the how fast core reset is there.
Switching frequency will be limited by first thing is your device capability, and no, because in one time period you need to do a reset once, right? Whatever the
Yes.
switching frequency will be, or whatever the time period of the circuit will be, you need to reset it in every time period. So it won't depend on the switching frequency. Switching frequency is generally limited by the losses, okay, and devices. So as you increase switching frequency, your losses in the converter will increase. So switching frequency generally limited by the losses and the device, whether the device is
So
capable to operate at such high frequency or not. Yeah.
during off time, the ILM it should come to zero for
Yes.
complete reset. So
Not
that
for
will
this
depend
circuit.
upon okay, not for this
It is for forward converter. Yeah, you are correct. Yeah,
forward
go ahead.
converter.
Go ahead.
In that case, forward converter. In that case, this LM is associated with some resistance, winding resistance. So that will limit.
Yeah, if you are designing a lossy forward converter, then that will limit. Yeah, because you see the loss there, half
Yes,
Lm
sir.
ILM peak
Correct.
square into frequency.
Yes, sir.
So,
Yes.
uh,
Okay,
okay,
sir.
so okay, thank you. So, coming back to your question, Aris, so there are certain things that we need to take care during the design. So, generally, we try to avoid all the spikes in the voltages. That spikes may come because of IDI by dt. Right? So we try to handle it, and yes, if it persists, then we will have to design the switches according to those ratings. That I agree. Okay. So is there any other final question?
Your email ID?
Yeah, I think I mentioned just before. You did not able you are not able to see that.
No.
Okay. I write it one. Now you get that.
So where it is written?
It is in
Ah,
chat box.
wait a second. Ah, JDS
Yes. Dot IITB
IITB @gmail.com.
a dot is placed between JDS.
Okay.
Okay then. So we will wind up the session.
Okay.
There are further. Thank you very much for joining the session. Nice.
Thank you. Good night.
Thank you.
Thank you, sir. Good night.
Thank you.
I will send you email, sir,
Definitely, definitely.
for that controller.
Sure, sure.
Thank you, sir.
Thank you.